Thanks, Roberto. Good morning to everyone. Can you see my slides? My volume is okay?
Yes, yes, yes.
Great. Okay.
Yes.
Okay, great. First of all, I want to thank all the members of the organizing committee for this exciting interdisciplinary conference on dynamics and complexity. It's my great honor to give my lecture within the memorial of Marcello Bugliatti. Unfortunately, I could not know Marcello Bugliatti personally, but as far as I know, he gave a great contribution, relevant contribution to genetics, and also he gave some relevant contributions also to the study of complex systems. A special thanks to Roberto Marangoni for his kind invitation. Roberto asked me to present a talk about the complexity in chemical systems. The subject is really vast, it's so vast that today I have decided to tell you how much chemistry and complexity science allied together can be valuable to tackle global challenges. Next time, I will tell more about complexity, other aspects of complexity in chemical systems. Okay, let's get started. One relevant purpose of science is to solve problems and improve the psychophysical well-being of humans. Nowadays, there are almost 8 billion people on Earth. Of course, each person strives to reach their psychophysical well-being every day. But beyond personal needs, our contemporary world is different because global challenges also need to be faced. The development of transportation means and information and communication technologies has transformed humanity radically. Humans are now more linked to each other than ever before. Humanity as a whole gives rise to a vast and very dynamic network on Earth. Every human being belonging to this network needs to face challenges regarding the network as a whole. And such challenges are global for two reasons. First, they might regard almost everyone on Earth. And second, they might be multisectorial because they encompass humanity from different points of view, such as health, social, political, economic, cultural, and ethical. Global challenges require global agendas to be faced and won. For instance, in 2015, the United Nations compiled a comprehensive and far-reaching plan, the famous 2030 Agenda. And this agenda includes 17 goals assuring a general sustainable development if pursued worldwide. At the heart of the 17 goals, there are human beings, their societies, the world economy, the urban areas, the natural ecosystems and all the living beings they embed, and the climate. These are examples of complex systems. Chemistry and complexity science play a relevant role in the comprehensions of the complex systems and in the attempts at controlling them. We are completely aware that chemistry is at the heart of human and animal health, biological environment, and physical environment. Chemistry must embrace being a science for the benefit of societies. On the other hand, complexity science scrutinizes complex systems through an interdisciplinary dialogue to pinpoint the features shared by all the complex systems, to propose adequate methodologies and methods for describing complex systems, and to look for possible new principles that rule the behavior of complex systems. Merging chemistry and complexity science helps to reach the goals of the 2030 Agenda and face any other global challenges of this century. All the complex systems involved in 2030 Agenda share some features. First, all complex systems can be described as networks, as the same Marcello Bugliatti said. And the constitutive elements of any network are nodes and links. The nodes represent the network elements, whereas the links are the connections between them. For instance, in a cell, the nodes are the molecules and the links are the chemical reactions. In our brain, the nodes are the neurons, whereas the links are the connections among synapses and dendrites belonging to different neurons. Alternatively, in an ecosystem, the nodes are the biological species, whereas the links are the symbiotic and trophic relationships among them. Different complex systems have distinct networks architectures. For most complex systems, nodes and links are diverse, and their behavior might be variable. Moreover, relationships are mutual. There are numerous feedback actions, positive and negative, and networks are characterized by high degrees of nonlinearity. Secondly, complex systems are out of equilibrium in the thermodynamic sense. If a complex system involves just inanimate matter, its behavior depends on the force fields. If a complex system includes living beings, its behavior also depends on the living being's power to use matter and energy to encode, collect, store, process, and send information to pursue their goals. Thirdly, complex systems exhibit emergent properties. A property is emergent when it belongs to the network as a whole. It cannot be attributed to a few nodes and links, but to the entire collection of nodes and relationships. Examples of emergent properties are the phenomena of temporal self-organizations, such as oscillatory chemical reactions and circadian rhythms. Spatiotemporal patterns, such as chemical waves and propagation of action potentials in a neuron's axon, which are examples of electrochemical waves. Another example is the transition from spatiotemporal order to deterministic chaos, as it might occur in the phenomenon of convection. Some of these emergent properties can be interpreted by recurring to nonlinear dynamics, but there are emergent properties that are not fully understood and cannot be predicted. The phenomenon of life is an example. Life has many peculiar attributes, as the same Marcello Buiatti revealed. However, we don't know the origin of life, we cannot obtain life from scratch, from its molecular constituents, and we cannot predict the evolution of its forms. So the question is, why are there emergent properties that are not understood and cannot be predicted yet? Well, there are at least three primary reasons which outline an epistemological complexity. The first reason is due to the descriptive complexity that includes the effective complexity proposed by Gell-Mann and Lloyd. Often, we encounter unsurmountable difficulties in describing complex systems by using the reductionist approach, because complex systems usually consist of many nodes which might be diverse and variable in their behavior. They consist of many links which might be diverse and variable. And all these features might be context dependent. In other words, some emergent properties of complex systems have the features of variable patterns. And variable patterns are entities or events whose recognition is made difficult by their multiple features, variability, and extreme sensitivity to the context. Examples of variable patterns are biological species, patterns and symptoms in medical diagnosis, patterns in apparently uncorrelated scientific data, aperiodic time series, political, social, and economic events. It's necessary to formulate algorithms that recognize every type of pattern, whatever their context is. And the steps of pattern recognitions are data acquisition by instruments, selection of the representative features, and application of an algorithm for the classification step. We still need to formulate universally valid and effective algorithms for recognizing all the variable patterns. The epistemological complexity is also linked to computational complexity. Many computational problems regarding complex systems are solvable but intractable. Examples are scheduling, machine learning, the Schrödinger equation, protein folding, the traveling salesman problem, and so on and so forth. Their intractability is understandable if we consider the theory of computational complexity. In computational complexity, a problem is a computational task coupled to a question. And an algorithm for solving a problem is a finite set of instructions or steps that guarantee to find the correct solutions to any instance of that problem. The steps of an algorithm can be addition, subtraction, multiplication, finite precision division, and comparison to numbers. It's useful to determine the function that relates the number of computational steps to the size of the problem, to have an idea of the running time of an algorithm solving a particular problem. A problem is easy if it is polynomial, if the number of computational steps increases polynomially with the size of the problem. You see here n is the dimensions of the problem, and the exponent k can be 1, 2, but never be the dimensions of the problem. The class of polynomial problems is the class of recognition problems, and all the polynomial problems are solvable and tractable. That means it's possible to determine the exact solutions in a reasonable time interval, whatever the problem's dimensions. However, there exist also exponential problems, problems for which the number of computational steps grows exponentially with the size of the problem itself. Unfortunately, these problems are intractable when n is large. Let's make an example and consider the Schrödinger equation used to determine the energy of a molecular system. The number of computational steps grows exponentially with the number of particles. When we have a system with just 500 particles, I say just because a macroscopic system consists of an Avogadro's number of particles at least. Well, with a system with just 500 particles, you see the number of computational steps is so huge that even if we have the fastest supercomputer in the world, which nowadays is the Japanese Fugaku, reaching the astonishing computational rate of 442 petaflop per second. One petaflop means 1 to 15 floating point operation per second. Well, even with the Japanese Fugaku, the time required for finding the exact solution of the Schrödinger equation for a system with 500 particles is so long, to the tune of 10 to 125 years, that is unreasonable. In fact, it's much longer than the age of the universe, which has been estimated to be 40 billion years. So clearly, we must abandon the idea of finding the exact solutions of large exponential problems if the only possible algorithm is that of brute force. Therefore, we are forced to transform the original exponential problems in problems of recognizing acceptable solutions generated non-deterministically and in a reasonable time interval. In other words, the exponential problems are changed in non-deterministic polynomial problems, or NP problems. And within the set of NP problems, there's the subset called NP-complete. It contains problems such as the Schrödinger equation, the protein folding problem. The NP-complete set embodies the secret of computational intractability, since a polynomial time algorithm for one of them would immediately imply the tractability of all the problems in NP. This would mean NP is equal to P. The exponential problems are reducible to polynomial problems. The Clay Mathematics Institute in Cambridge has named P versus NP as one of its millennium problems. And it offers $1 million to anyone who provides verified proof that either the NP problems are equal to P problems or this reduction is impossible. If the relation P equal P were demonstrated to be true, then, as the same Gödel said in a letter to von Neumann in 1956, that discovery would have consequences of the greatest magnitude. Our life would not be the same. Everything would be much more efficient. The transportation schedules of all forms would be optimized, allowing people and goods to move quicker and cheaper. Manufacturers and business persons would improve their production processes and increase profits. It would become much easier to find new effective treatments for incurable diseases, make weather forecasts, predict catastrophic events and the trends of stock markets. But even if one day someone demonstrated that all the exponential problems are reducible to polynomial problems, and universally valid and effective algorithms were formulated to recognize variable patterns, certain limitation in predicting the behavior of complex systems would remain. As far as the microscopic world is concerned, the Heisenberg uncertainty principle holds. And the uncertainty principle shatters the deterministic dream of predicting, of describing the dynamics of the entire universe, starting from the description of its microscopic particles, because it fixes an unsurmountable limit in determining accurately and simultaneously two relevant features of any particle, such as its position and momentum. We might think of limiting the description of complex systems at the macroscopic scale, neglecting their microscopic constituents. However, complex systems can exhibit chaotic dynamics, and chaotic dynamics are aperiodic and extremely sensitive to the initial conditions. Since the determination of the initial conditions of any system is always tainted by unavoidable uncertainties, we infer that chaotic dynamics are unpredictable in the long term by definition. So in summary, the reason we find unsurmountable difficulties in describing and predicting the behavior of complex systems are descriptive complexity, computational complexity, and intrinsic limitation of the predictive power of science. And being aware of these limitations that define an epistemological complexity, how can we reach the goals of the 2030 agenda and face any other global challenge that this century can reserve us? Well, I propose some strategies. First of all, we need an interdisciplinary approach in research and teaching. The formation of truly interdisciplinary research groups should be favored by public and private funding. It's urgent to propose interdisciplinary courses on complex systems, teach the theories that have some transdisciplinary features, because they break down the traditional disciplinary boundaries. And we should present the properties of complex systems. For example, this is what I propose at my university. I have written a book titled Untangling Complex Systems, a Grand Challenge for Science for my courses. And in this book, I present the properties of complex systems by dealing with subjects of chemistry, physics, biology, ecology, economy, and also philosophy. Mainly, I exploit the theories of non-equilibrium thermodynamics and nonlinear dynamics. I'm also participating in the European project of strategic partnership Erasmus+, whose aim is to enhance higher education on complex systems thinking for promoting sustainable development. Second strategy, the description of complex systems as networks must be carried out by using not only the reductionist approach, which focuses on single nodes and links, often is inappropriate, but also the systemic approach, which focuses on the entire network, and in some cases the mesoscopic approach, which focuses on clusters of nodes. Moreover, when we study complex systems, we cannot trust in a cornerstone of the original scientific method, which is the reproducibility of our experiments. Often experiments regarding complex systems are historical events. In this regard, the image that the philosopher Karl Popper has proposed in his essay titled Of Clouds and Clocks is particularly effective. In the past, science had been occupied with clocks that are simple deterministic systems having reproducible behaviors. Now instead, science has to deal with clouds that are complex systems having unique and hardly replicable behaviors. Furthermore, the investigation of complex systems requires monitoring complex systems continuously because their behavior is rather highly dynamic. Therefore, it's necessary to collect, process, and store massive data sets, the so-called big data. Moreover, it's becoming evident that an alternative way for doing experiments on complex systems is to perform simulations in computers. For these two last reasons, it's necessary to speed up our computational machines, extend their memory space, and contrive more effective algorithms. I think there are two relevant strategies to succeed in reaching this fifth goal. The first strategy consists in improving current electronic computers that are based on the von Neumann's architecture. The pace of computers' improvement has been described by the Moore's law, stating that the number of transistors per chip doubles every 2 years. However, Moore's law will stop holding sooner or later because transistors will be made of a few atoms. Chips producers invest billions of dollars in contriving computing technologies that can go beyond Moore's law. The second strategy is the interdisciplinary research line of natural computing. Researchers working on natural computing draw inspiration from natural phenomena to propose new algorithms, new materials and architectures to compute and store information, and new methodologies and models to interpret complex systems. Natural computing is based on the rationale that any distinguishable physicochemical state of matter and energy can be used to encode information, and every natural transformation of these states is a kind of computation. Within natural computing, there are two important research programs. In the first research program, one exploits the physicochemical laws to make computations. Every physicochemical law describes a causal event, and any causal event can be conceived as a computation. In fact, the causes are the inputs, the effects are the outputs, and the law governing the transformation is the algorithm of the computation. The second research program on natural computing mimics the features and performances of the natural information systems that belong to living beings, to living systems. We might mimic living cells, or nervous systems, or immune systems, or the societies. All these systems are capable of exploiting matter and energy to encode, collect, store, process, and send information. Currently, my attention is focused on the neural information system. The human nervous system, which has human intelligence, we might say as its emergent property, is significant when facing complexity. Human intelligence allows us to handle both accurate and vague information, computing with numbers and words. It allows us to reason, speak, and take rational decisions in an environment of uncertainty, partiality, and relativity of truth, when the incompatibility principle holds. According to this principle, as the complexity of a system increases, accuracy and significance become almost mutually exclusive characteristics of our statements. Finally, human intelligence allows us to recognize quite easily variable patterns. Therefore, by studying human intelligence and trying to reproduce it by developing artificial intelligence, artificial intelligence is revolutionizing our lives and societies. It's using basic and applied science, medicine, well-being, economy, and security. There are two principal strategies to develop AI. One strategy consists in writing human-like intelligent programs running in computers or special-purpose hardware.
Pierluigi?
We lost your sound.
Not hear you. Oh, okay.
Hear me?
Okay, yes.
No.
Okay. In neuromorphic engineering, surrogates or neurons are implemented through non-biological systems, either for neuroprosthesis or to design brain-like computing machines. Surrogates of neurons can be implemented through specific solid materials in hardware, and such hardware can be rigid if made of solid inorganic compounds, or flexible if based on organic fields. Alternatively, surrogates of neurons can be implemented in wetware through solutions of specific nonlinear chemical systems. Finally, there's the possibility of using hybrid electrochemical systems. In our group, we are working mainly on wetware. We propose the use of molecular, supramolecular, and system chemistry to mimic some performances of human intelligence and develop chemical artificial intelligence. Specifically, we are devising modules for futuristic chemical robots. A chemical robot is thought of as a molecular assembly that reacts autonomously to its environment through molecular sensors. It makes decisions by its intrinsic artificial neural networks and performs actions upon its environment through molecular effectors. The intelligent activities of a chemical robot should be sustained energetically by a metabolic unit. Chemical robots should be easily miniaturized and implanted in living beings to interplay with cells or organelles for biomedical applications. They should become auxiliary elements of the natural immune system. So far, we have devised sensory modules. For instance, recently we have implemented a photochromic system that extends human vision from the visible to the UV. We are contributing to the implementation of artificial neural networks. We propose specific chemical systems to mimic neural dynamics and investigate phenomena of temporal synchronizations through optical communication. We are also proposing strategies for the chemical implementation of fuzzy logic. Finally, we are developing effector modules, for instance, an artificial gland that is a composite system made of a pH-sensitive hydrogel and a dialysis membrane. To succeed in our project, we follow a methodology that has been declared effective for dealing with any complex system by the cognitive scientist Gallistel and King and the neuroscientist Marr. Such a methodology requires an analysis of a complex systems at 3 levels. The first is the analysis at the computational level, and it consists in describing the inputs, outputs, and the computation that the system performs. The second is the analysis at the algorithmic level, and consists in formulating algorithms that might carry out those computations found in the previous level of analysis. Finally, the third is the analysis at the implementation level, that consists in looking for mechanisms that implement the algorithms. So, as a general conclusions and perspectives, we might declare that complexity science and chemistry allied together can contribute to reach the goals of the 2030 agenda. In particular, the research line of chemical artificial intelligence can implement modules for chemical robots that will play biomedical actions. Secondly, the chemical artificial intelligence proposes new materials and architectures to compute, new algorithms to face computational and descriptive complexity. Good results in this direction would have a positive impact on the economic growth. Third, trying to obtain intelligent chemical systems from scratch can help to understand what is intelligence, but also what is life. The appearance of life on Earth was a phase transition, can be described as a phase transition or sudden change in how chemical systems can process and use information. In the beginning, the world was abiotic, and any chemical matter was unable to process information. Then about 4 billion years ago, the phase transition from a purely abiotic to a biotic world occurred. What happened at that time? A deeper understanding of these emergent properties, intelligence, and life will contribute to unveiling natural complexity from an ontological point of view. Finally, I acknowledge my collaborators, my young resources that helped me to reach the results, some of the results I show you today. And finally, I acknowledge also the agencies for funding and all of you for your attention.
Thank you.
Can I make a comment?
Interesting and also challenging talk. Questions?
I would like to make a comment and also a question. If first of all, I would like to express I'm very impressed, Pierluigi. You did a remarkably good talk, very exciting. I liked very much. You see,
I second that.
congratulations, congratulations. But I have a question that to see if I understand, which has to do, in fact, with chemical reactions. I would like to ask you a question about Karplus, who has been studying enzyme reactions, and which I myself, 30 or 40, 50 years ago, I was interested in enzyme chemistry. But Karplus, who got a Nobel Prize, by the way, claimed, well, chemical enzyme reaction are understood, and when you say, can you explain to us, I say, I can run my computer and I can explain them. So, in other words, the computational issue can be interpreted as an understanding, because I myself, I don't understand yet enzyme reactions, because I would like to use, you mentioned phase transition, I would like to go through that approach, but I would like to get your opinion about that.
Yeah, I really trust in this approach. In other words, in the natural computing approach to read natural phenomena. So I trust in this approach, and I think it's really promising, especially if we want to face the kinds of complexity that I told you define the complexity from an epistemological point of view. In other words, if we want to find effective solutions to the problem regarding computational complexity and descriptive complexity, I think it's promising to read natural phenomena with the lens of natural computing. In other words, we interpret every kind of natural phenomenon as a computation. And clearly, of course, chemistry offers a lot of examples, valuable examples that can be exploited to propose new, let's say, computing systems, new algorithms as well.
Okay, thank you.
It's a pleasure. Thanks for your comments, positive comments.